Hi, everyone. Thank you for joining us today for Deploy the Matrix. This is the part 2 of the Let's Make a Cloud App with .NET series. Before we start, just a few quick things to review. Please take a moment to read our code of conduct. We ask that you be kind and respectful to everyone, including our speaker. We want all Reactor sessions to be a place where people feel welcome. Please ask questions using the live YouTube or Twitch chat. In the chat, we'll also be sharing some links to our Reactor meetup page and monthly newsletter if you're interested in checking out what else we have coming up. If you haven't already, please check in using our event check-in at aka.ms/reactor check-in with event ID 14751. By checking in, you'll receive links that go along with today's content. We'll also be adding this session to our Reactor YouTube page in 24 to 48 hours. Finally, towards the end of the session, I will share a link to our Reactor survey. If you have a few minutes, we greatly appreciate your feedback. I will now pass it over to Sam.
I'm Sam Wronski. I am a regional cloud advocate here at Microsoft, focused on the Bay Area. So my job is to help empower everybody in the Bay Area and then the broader Microsoft developer group to build awesome things. So what we're doing today and what we've been doing or going to be doing this month is building an app that can transform a set of points into some new set of points for us. The intention is to kind of walk through how you might build a cloud data processing pipeline app. So we're taking a bunch of looks. This is a live coding thing, which means that a lot of this is sort of intended to show my learning process as much as showing a solution to this. So I've built like apps like this before, but not this app before. So that's sort of what we're walking through. Previously, we set up a GitHub project. So we have a public GitHub project, and we also have some basic code set up. We have a code library and some tests. Today, we're going to be focusing on the actual brains of this entire application. We're going to be focusing on how we can actually do some translations, which is moving it left, right, and up and down, rotations, which is the hard one, and then scale, which is making the points bigger or smaller. In this case, each of the points is on the edge of this cube. For this demonstration, we're actually going to be scoping this down even further to just do a two-dimensional shape. The logic is all the same, but there's less math. So we don't lose anything. We just don't have to do as much complicated math. We don't have to create as complicated formulas in order to accomplish the same thing. We just won't get three-dimensional rotation, which is sort of the hardest part of this. So each point in this cube, we're probably going to be working with just a square or a rectangle or a quad, as they're sometimes called. We're going to be translating that and creating an application that can manipulate that. So something will feed us in data, kind of going to sort of where we sit in the infrastructure of this whole thing. We have a series of requests for transformations in a queue. Our application is going to pull those requests off, perform the transformation, and publish them back onto the queue so that whatever is downstream can work on them. This might be useful, for example, if you have a upload system where somebody uploads a mesh and you need to process it, or uploads a video and you need to process it, and then you want to publish the processed version. That's sort of the thing that we are building here. Highly encourage you, drop any questions you have. This is intended to be a longer stream so we can take those detours and kind of do that learning process together. So if there are things that you think we should explore or try, or you have suggestions that would make this app better, feel free to leave those. That's exactly what we're looking for. So anyway, we're going to get started. I have done one thing off stream, and that is add the project to a solution file. So we have access to Visual Studio 2022. So this is our solution in Visual Studio 2022, so we can actually start playing with this. We have a test explorer. Disclaimer, I'm not a big user of Visual Studio recently. I've been working in other languages that just haven't had Visual Studio support. So we're going to learn that together as well. So what we need to do is implement these tests, because we just have one unit test that tests if 2 + 2 is 4. which is great, but it's not actually useful. And we have this class which is empty. So what we're going to do is add a bunch of different data types that we can use to actually process a lot of this. So that's largely what we're going to be doing today. And then tomorrow and the day after that, we're going to be focusing on how do we actually process this with a data pipeline, and how do we actually add some CI so we can actually get this continuously publishing. So we actually have constant updates in the cloud, so our application is constantly deployed. So we're going to actually just start creating things. So we're going to create a few classes here. The first one is just going to be a mesh. I don't have these classes planned out, so we're just going to kind of implement them. Because we don't have a strict contract on either end of our queue right now, we can actually kind of tweak this as we want. We don't need to architect our application to fit a specific contract. We don't have to do that. So instead, we're going to kind of add fields and properties as we need them to kind of do that and explore our architecture a little bit to find something that makes sense. So we might be coming back to these as we go. So we have an internal class called mesh. What we want to do is probably make this public. If you're unfamiliar, there are different access levels in classes. There's private, protected, internal, internal, protected, internal. I forget which order those are in, and then public. The way this works is you have public means that the class is publicly accessible. So anything that includes this library is going to have access to it. Internal means only the things inside of this library would have access to it. Protected, only things that inherit from it. And private, just the class. And then internal protected is anything that inherits from it externally. So if you have a abstract class and things down in dependent projects are inheriting from it, they would be able to access those internal members and work with them. So let's just add some public stuff. We're going to work again with 2D vectors. So I'm just going to call this a vector2. It doesn't exist, but that's fine. And we're just going to make this a list, I think. And let's call this points. Hardest part of this is figuring out the names. So we're just going to call this a set of points with a getter and a setter. We probably don't need the setter. We probably actually don't want the setter, but it's going to be there. And so this creates a property for us that has this list of vector2s. Vector2 in this case is sort of shorthand. It's commonly used. If you're familiar with game development, you've probably seen these before, but it just stands for a two-dimensional vector, which just holds 2 points. So 2 floating point values. And so we need a vector2. I think I might end up using some Visual Studio Code hotkeys and then get very lost, but we'll see what happens here. Generate type in new file. There we go. Awesome. So we have a new vector2. Let's add those 2 properties, a public int, probably not an int, a float of x, which is going to have a getter and a setter, and a public float y, which is going to have a getter and a setter. A lot of the times I've seen these implemented as structs. We're using classes here. In our case, it probably doesn't matter. There might be some advantages to using structs just because they'll be better for this. But we're going to use classes for now just because that's what I'm familiar with. And we can always go back and refactor that. That isn't a difficult refactor. So let's do private set. We might actually want these to be init. So init is a new keyword, one that I am not actually very familiar with. So let's actually go and figure out what that does. So .NET init is a new property keyword that you can specify for property accessors. So this is used when you're initializing a property. So there was previously get and set, and then init is a new one. So if you are initializing that property for the first time, that is where init is going to come in, and you will actually be able to provide a value there. So that should give us what we want. This effectively will make this read only. So we shouldn't need to worry too much about that. That's one of the values that we might get out of a struct. So for mesh, we have vector2. Now we need to actually do some things with these because these aren't actually doing anything. They're just data objects. We actually want these to be able to do some math. So the first two things we want is probably an operator add, which I don't remember how to do operator overloads either. So let's go and figure out how to do that. So operators and expressions, I think it's just right here. There we go. Plus. Oh, that's a different thing. So let's do .NET operator overloading. There we go. Go and figure out how we can do operator overloads. The way this works, if you're unfamiliar with C#, operator overloads are supported, which allow you to override different operations of a class. So adding things like two strings, if you're trying to concatenate them with a plus sign, that is an operation. That's the plus operation. So we can override those and tell it to do specific things for the data type that we're working on. So in this case, it looks like it's operator plus and the two classes with a public static. Awesome, cool. So public static vector2. We got operator plus with two vectors. So vector2 left and vector2 right. This is just a naming convention that I've been using. I don't know if it's the best, but it seems to work. So that's what we're going to do. Not all code paths return a value. That's correct. So we're going to return a new vector2 with a left.x plus right.x and left.y and right.y. And I've already typed this wrong. Perfect. So we're going to just do that, and then we're going to actually go and test this. So we've written our first operator. It should work. We don't have a constructor for this, so let's do that. Public vector2. And let's just do a float x and float y. That gives us the two values for this. And then we're just going to initialize this with x equals x and y equals y. For me, I like to put this in front of the assignments here, just as a pattern here. Again, these things are kind of whatever makes sense to you. But for me, I like to do this because I tend to name my variables without underscores or even capitalization if they're just variables. And so in that case, I've constantly found myself naming things the same thing. And this avoids any complications with that of saying like x equals x, which doesn't do what it might appear it does, which is assigned to that. It doesn't do that. So this gets rid of that. All right, so we have our operation plus. Let's actually implement some tests for this. So let's just do some vector2 test. If you're unfamiliar with testing or unit testing or just software testing in general, the goal here is to create some way to automate the validation of your software, to provide proof or give you some reassurance that the code you're writing works. It's not always clear that it's going to work, and it's not always obvious that things are working, especially in a larger project where you have not written all the code. You may not know what everything is supposed to do. So what unit tests can do is actually explicitly say, for this situation, this is the result that should happen. And you can use this to sort of define the behavior of your app. Some people will define the test beforehand. I found that when you're defining the initial features of your product, you can actually include some general tests that kind of outline certain things that need to pass for that feature to be complete. In this case, we're just going to be testing our vector2 to make sure that it actually works. Vector2 addition test. So what we're going to be doing here is just testing that addition that we did. So we have a vector that we need to add. The general pattern that I use when writing these tests is sort of I guess, spoken one where you do given something, when something happens, expect some result. And so the given is the initial values of the thing. The when is the operation that you're testing, and expect is sort of the outline. Hello, deflux K. I don't know if I'm pronouncing that right, but hello. Yes, hi. It's me. Given, we're just going to do some really basic operations here to kind of get started with this and start adding some basic vectors. So let's just do vector 2. We actually need access to this because we didn't do that. So that's important. So we have this public vector 2. It exists here in our matrix mesh math. Let's make that a file scoped namespace. We talked about these a little bit on Friday, but what this is a namespace that applies to your file. So if you're familiar with Java, similar idea. What this is doing is giving a namespace kind of across the entire file. So you can't define additional namespaces in here to kind of wrap things in other namespaces. But what this does do is if you're constantly creating a namespace for a single class, like we're going to be doing here, this will encapsulate it in that namespace without having to do all the indents so you don't lose all that white space. Let's figure out why I can't access my thing. It might just be that I haven't built it. I'm not entirely sure. So we're going to figure out, what did I click? We want to add a dependency. Project reference. Let's just go to dependencies. Add a project reference. There we go. And we'll just add our matrix mesh math. There we go. And so now, hopefully, our tests actually know what I'm talking about. So we have vector 2 here. Let's create a new one. So var left equals new vector 2. And we're just going to start with something relatively basic here and just do var equals vector 2 and just add 2 empty vectors. And we should expect so var result equals left plus right. When we add these 2 together, we should still get 0. Do I stream? Yes, I do a few streams. I kind of produce a lot of content. I've actually been focusing a lot on the stuff that I'm doing for the reactor. For those that don't know, I actually recently joined the reactor back in July, and so I've been kind of focusing a lot on doing a lot of this stuff and trying to cover a lot more cloud-based stuff because I think that this is just super cool. As you can see, we're kind of integrating some game dev stuff, which I've done a bit in the past, and we're actually going back into game dev in January. So if you're interested in that, we'll be able to go into that a little bit more. Result, left and right. And then our expectation is that our vector 2, our result rather, is equal to a new vector 2 of 0, 0. And this probably is not going to work. I'm not entirely sure. I think this should fail because we haven't written an equality operator. So there's no way for this to know that the things are equal. And so I think it's going to compare the reference, which should be different. But I could be wrong. And we'll see what happens then. So let's run this. There is just this fun test explorer, which is awesome. I think we might even be able to do some cool things. Repeat last run, run failed test. I remember there being something that I don't know where it is or how to do it. Configure run settings, auto detect run settings. All right, we'll figure that out later. This failed, which I expected. Our assert equals did not work. You can see down here, assert equal failure with an expected result of x equals 0, y equals 0, and the result of x equals 0, y equals 0. It should have worked, but this is an equality comparison, and we don't have equality in this at all. We're not doing that. So let's get rid of that class because we don't need it. In this case, we actually probably want to add equality and the equals operator. So public static vector2. I don't think that's the one we want. Bool operator equals. Let's just, I think it's equals. So this is interesting because I don't typically implement these. So let's figure out what I need to do. I think it's override equals. There we go. If this equals base.object. So if I don't actually know the pattern for this. There's probably a pattern for this. I'm going to kind of make up my own and we'll see if it works. And if it doesn't, then I'll go and figure that out. That's just how I like to do this. It helps me learn a little bit if I try something before just going and finding a solution. So we're going to try is say if object is vector2, and we're going to say vector. That's going to be the name of this. This is using pattern matching in .NET. So what this is doing is saying, is object a vector2? If it isn't, it's going to return false. But if it is, it's going to return true and assign that cast vector2 into this vector object. So we now have a vector of whatever this object is as a vector2. And we can just use that to create our comparison. So we're just going to return vector dot x equals this dot x. And I think if you want, you can also write and. That's a separate thing, but there's also an and operator here, which we, if we wanted to, I think we could write this code shorter. Is what I'm trying to get to. Vector dot y equals this dot y. And so we're going to just kind of test for equality here. And so this hopefully means our test will pass. There we go. Awesome. So we now have a passing test. So adding 0 and 0 together, it's a 0, which is good. It means that we did nothing correctly. So let's make this a little bit more complicated. And to do that, we can just go and make another test. So let's create another fact here of the addition test 2. And let's, in this case, add 1 and 1. This should fail, so we should get 2 here. I'm intentionally testing basic things and trying to target edge cases. We're going to not be super concerned about out of bounds errors, because if you're doing that, weird things are going to happen. We might want to put a test in to figure out what the behavior is for that and kind of explicitly define that. But for now, I'm going to leave that behavior undefined because the expectation is that doesn't happen. That's maybe not the best solution here, but for now, that should be good. So in this case, 1 plus 1 should equal 2. Again, seems relatively simple. That's sort of the intention here, but we're covering different paths. 0 and 0 is a separate case because we're not actually adding or removing anything. In this case, did that not run? There we go. Let's just run that. This test should fail because we actually got y equals 0 because I sneakily put in a wrong value here. So left.y minus right.y. So we're actually taking 1 plus 1 and then 1 minus 1 and messing up. This gives us a way to detect these things because in thousands and thousands of lines of code, it's not always obvious that even these simple things happen. That was just me being sneaky, but I thought it was fun. So this should pass now, and it kind of shows us that our code is working, which is good. So we now have working things. So that is our addition. Let's add multiplication. And these are sort of the core things that we need in order to support scaling. So we're going to add support for addition, subtraction, multiplication, and division here. Our application might actually not need subtraction and division. So maybe we leave those out for now and we come back to that. But in this case, let's just do multiplication. And these are intentionally simple functions. They're intended to be something that is not super complicated. Like we're trying to keep these focused. One of the advantages of testing in general is you want more tests. These smaller in scope your tests are. You might see a testing pyramid, which is you have this small little point at the top, which is your end-to-end tests, and the middle bit is your integration tests, and then the very big wide bottom is all of your unit tests. Generally, figuring out the classification is a little bit fuzzy. At least I found it to be. And so I tend to look at what is the scope of the test. The reason for that is because the introduction of tests is introducing technical debt, or it can introduce technical debt. As your application changes, every test that is covered by the code change is affected as well. So you increase the difficulty of a change, the more tests you add. And so by creating very specific focus tests that tell you, yes, this feature works, rather than the application works, you get more targeted and directed feedback on what's broken and what's working. This is kind of nice, especially in this case. One of the cool things you can do with tests is figure out exactly where the errors are. If you're just running an application and it's not working, the only surface area that you have when you're testing it like that is the user interface, or however you interact with that application. It's that barrier. With unit tests, you can dive deeper and actually figure out, does addition work? Does subtraction work? Does multiplication work? And that can be a really powerful tool because it's typically not the granularity that you would expect to get access to if you're just testing generally. Anyway, I'm going on and on and on about things, but that is, this is going to be a cloud app. So haven't actually figured out what platform we're going to put this on. I think this would be a really good use case for Azure Functions. So we might explore that. If there's suggestions on things that you would like to see, we can go in that direction. I've intentionally kind of left this open. I have a Kubernetes cluster. We could go down Kubernetes and kind of make this as a service that just has a data processor. Or we could go down Azure Functions and create a function that reads off of Azure Service Bus. We'll be implementing that tomorrow. But for now, this is intended as sort of a cloud application to pull in data, process it, and publish the new results. So operator multiplication, left and right, return new vector 2. And we get to do all the fun, boring bits again. One of the features that we might be able to use if we come back and refactor this is records. It's a feature that is relatively new. Added in C# 9 or 10, I don't actually remember. But it is a reference type that can do equality and things for you out of the box. So it does just all of that for you. Very cool. You use them with like record vector 3. Let's just say that float x, float y, float z, and that creates a struct that, that creates a type that would hold x, y, and z as a read-only value type. I think it's value. I'd have to double check. But they're relatively new. It didn't quite make sense when I was thinking about it to use them here because we're adding all of these processing things. So I have avoided it, but that might be something that would be fun to look into. Anyway, I'm getting distracted. That's sort of the intent, but also, yeah, let's focus a little bit. So vector 2 tests. Let's add another test. That was our addition. Let's just do multiplication here just to make sure that's working. Multiplication, and we want to have our vectors. Let's do that and multiply 1 by 1. So this should give us a result of 1. So we're multiplying a vector of 1 by itself. And so that should give us just the end result of whatever that is. So let's run this test and see what we get. Hopefully they all pass. Good. So we now have working addition and multiplication. I say working, I don't actually know if they're working. So we have a few tests, but this isn't by any means an exhaustive list. There can be a whole bunch of different things. So I think what I want to try to do is explore something else. What are they called? This might be a quick exploration in my Google foo. So we're just going to go and do XUnit data-based tests. We have a series of tests, and what we're doing is we are inserting new tests constantly. So we're just going to go and find this random blog post. Here we go, theories. That's what we wanted. So we want theories to test this. Theories are an XUnit feature that allow you to do cool things. So let's leave that as it is and go up here. Theory, and we want inline data. And now what we're going to do is provide some data. What a theory is a test template. I think that's the best way to describe that. Different testing frameworks have this functionality. If you search for what I search for, which is like data-based test, for whatever framework you're looking for, you should find it. This isn't a .NET thing. This isn't even an XUnit thing. This is just a tool to make your tests a little bit nicer. So in this case, what we're going to do is define a set of data that includes the left, right, and expected results for each of these things. And then we can just test addition that way. So in this case, we want 0, 0, and 0, 0. And then the expected result is 0 and 0. So that's going to error out because there's no matching parameter here. So let's add them. Left X. This part gets a little bit verbose, but we're just going to go with it. Left Y. And then right X and right Y. There we go. And result X and results. Here we go. Results Y. Cool. Awesome. So again, it's a little bit of data. You can also pull this from, I believe, like CSV files or other databases. So if you want to define tests in an actual table or something and make them a little bit easier to use, that's an option as well. We're just going to define them like this. And now we no longer have a compile error here. And then what we can do is actually use these. So we can do left X and left Y and right Y and right X. And then our result is just going to be the results here. So result X and result Y. All right. Now we've finished all of the annoying typing bits. So we should be able to rerun this and get results. It might appear a little bit different here. Yeah, okay. Let's see if I can make this a little bit easier to see. There we go. So we actually get the values in our test explorer that say left X, left Y, and so forth, and actually tell us what those values are. And now we can just delete this test. What we're doing 1 + 1 is 2. We can just get rid of that. And instead, just add another piece of inline data. So we can do 1, 1, 1, 1, 2, and 2. I don't think I'd have to test this. So we can do that with the multiplication, but I don't think you can actually include structs here or classes in this definition. I'd have to check. We'll find out. Anyway, we now have 2 tests here, and we deleted however many lines of code that was, like 14 or something, and just have 1. And the cool thing is, this means that as our test chains, maybe we have an add function, we can insert that and use the same data to run the same tests without having to include a whole bunch of things. So this gives us a little bit more. We actually get an extra nested part in our tree that shows both of the things that are being tested. And so now we can actually add a few extra tests. So we can actually test this and make sure that things are working. So we have addition, we have nothing. Let's also do something that is just on the 1 vector. So in this case, we're going to expect a no op from each of them. So I'm going to add 4 different distinct tests here, just to make sure that each of the values from each of the things is carried over correctly. And again, testing is largely a feel-based thing. I don't know if that's the best way to describe it, but that's how I'm going to describe it. A lot of it is figuring out what the goal is and figuring out where or what questions you're trying to prove and what you're trying to say about your application. In this case, we're saying if you add certain things, you should expect the result to appear in the correct place. There we go. What I'm saying here is you should expect the result to show up and be sort of the definition of your application's behavior. Tests are a very good documentation source for an application. If you're just joining a new team, for example, look at the tests. They can tell you a whole lot about what the application is supposed to be doing, and typically in a more clear way than just looking at the implementation. That's a lot of the ways that I onboard when I'm trying to learn, is finding the tests for the whatever thing I'm interested in and diving into those. So we have a bunch of more tests. Let's just run all of these. This should hopefully give us a little bit of confidence that our addition is working. It's addition. We didn't do super complicated things here, but this is really useful for those more complicated features as well. Part of the cool thing of doing these vectors and matrix stuff is that we're kind of focusing, there's math involved and potentially some complicated math, but it's not a lot of actual coding. There's not too much here to kind of trip us up and get us lost and just spend a bunch of time typing. So let's do this new multiplication. Let's see if we can do this. So let's do a new theory here. Just look at our multiplication. Let's make our names the same. So we're just going to add test to the end of all of our tests, just so there's some clarity there. And let's do some inline data. So for this, I'm going to try a new vector 2 of 1 and 1. And we're just going to see if this works. I suspect it won't, but I would be happy to be wrong. That's also there. We're doing multiplication, not addition. Cool. All right. Must be a constant expression. Yeah. Okay. So attribute blocks expect constants, and these are not constants. They are classes. So they're references. Which is not a constant value for us. So we actually need to provide the values like we had up above. So we're just going to do that quickly. There we go. Cool. Awesome. And then let's copy some of this again. And we can actually just take all of that. If I press the right buttons, there we go. Cool. All right, so we have our left, our right, and our result, which we want here, which is a new vector 2, result x, and result y. So hopefully all of the typing is done. We don't need to do addition, or we're going to skip over division and subtraction. That's a little bit extra that we can just kind of not worry about. And instead we get this. So multiplying 1 and 1 gives you 1. Let's add a few others. So let's say multiplying by 0. What does that give us? That should give us 0. And we can do this on either side. So what I like to do is with tests like this is invert things. So in this case, we have x and y. They should be doing the same thing. But we need to test that they're doing the same thing because that isn't actually guaranteed. Like we saw previously, I had subtraction in one of them and addition in the other. And so typically, this is a nice way to kind of iterate on tests and expand those test cases so you just get good coverage over different paths that your code can take. A lot of the conversation with tests will typically go around edge cases. which are sort of the cases at the boundaries of what things can do. So I had mentioned 0, for example. That's a useful edge case because it's actually a no op. There's nothing going on there. Another one is way out near infinity. If we were concerned about that, you would run into issues with what happens when you multiply the maximum float value by 2. And do you care? Does your application crash? That could be something that you might want to test just to like create a concrete behavior. Not all of these tests need to pass. That isn't the thing here. They don't all have to be the happy case like they are here. They can be failures where you try to multiply something by something that doesn't exist. That can be a thing if that's something that your application relies on. So just things to think about. But anyway, hopefully we have working tests and we can kind of move forward and start actually doing some of this stuff. Because what this is, what we've done by adding addition and multiplication is actually 2 of our translation and scale. So if we're talking about our cube here, if I just set this back to 0 because that just makes more sense, scale here is just multiplication. We're just taking all of the points centered around the origin of that mesh and multiplying them by a set amount, and by whatever that vector is. For translation, we're doing the same thing. We're just we're adding all of for every point in the mesh, we're adding some fixed vector to that. And then the other one is rotation, which we'll get to at the end because rotation is hard. Rotation is where we get into like linear algebra. Typically, I was going to look at doing all of these with matrices because you can. That's typically how this stuff is done. If we're talking about graphics, but matrices are a lot more complicated, and we did this more efficiently, I think, and also more simply just by sticking here. So different trade-offs. So of all of this, let's do some other stuff. So we have our mesh. Let's actually create some operations here. So one of the considerations for a lot of this stuff is how you're going to actually interact with your data. In this case, we used operator overloads to add and multiply our vectors. The other thing you can consider is how you're going to interact with your meshes or your other data objects. This can actually define a lot about your application. So in this case, we have our multiplication and addition. We want to perform these operations across a mesh, which is going to be a set of points that are defined in space. And so what we could do is just add multiplications, public void. We probably actually want this to be immutable. So we're going to just do public mesh set. We'll make that in init again. Init on a list gets weird. So that may not actually be as helpful as I'm kind of pretending like it is. But we're going to do it anyway. I say that because the read-only part of this, the part that you can't set, is the list. That's not going to prevent you from clearing it or adding new entries or removing entries or anything like that. That this is still just the list object is the readable thing. So we could do public mesh and do scale and give it a vector 2 by the scale amount and just go through and multiply all of them. We can actually just write that out now. And we'll talk a little bit about the different paths. If anybody has suggestions on which direction they would prefer we take, let me know. Because again, this is intentionally being kept kind of open so we can take those different paths and figure out which way to go. So scale. What we want to do is just kind of iterate over all these. Let's create a new results list. So list 2. I don't know what I'm doing. There we go. Results equals a new list. All right, we got there in the end. The hardest launch code. Okay. Anyway, ignoring whatever that was and the fact that I forgot a semicolon, let's just do for each var point in our points. So we're just going to iterate over every point in our mesh and multiply it by the scale. So our results equals point. Let's just do point times our scale. And there's the new point. Why doesn't it like this? Oh, that's why. We need to actually just add this. There we go. Trying to set that to a list isn't going to work. Cool. All right, so we add this, we get our points, and now we've effectively added scaling for our mesh. The thing with this is that we are now turning our mesh object from a data object that is storing information about the mesh that we're talking about, the data that we're transmitting. We're turning this into I don't know the best word for this, but we're turning it into something that's actually performing business logic. This is an actual thing that we might need in a business. What you end up doing or at least what I've had happen with my own apps when going down this path, is you end up with thousands of lines of this, because what you've done is you've implemented every new business feature that you need in your data object, and the next one just gets tacked on. This can make it really hard to actually understand what this thing is about. Typically, classes are better, or at least I find them to be better. The smaller and more concise they are, the more clear the scope is for them. And also separating your data from the logic can actually really help you as far as like testing goes and as far as everything else goes. So in this case, I'm not super worried about doing the vector 2s. But for the mesh, for example, what if we want to add a filter that removes duplicate points? So if we have 2 points that are the same and we want to pull the second version of that out, how do we implement that? Do we just add another function here? And then as we continue to add things, how is that going to work? How do we want to actually handle that? So that's sort of one of the considerations we have here as far as the architecture of our application goes and what decisions we're making here. So anyway, that was a really long talk about design. So let's just do a new mesh here with our points, results, and we'll get this. We need a semicolon. There we go. And now let's figure out what we actually want to do here. So we have our mesh with our points. I'm intentionally doing this as it will produce something new instead of mutating it in place. I find that that's more useful. And typically what people want, because a mesh or a class rather is a reference type, meaning that as you pass it through your application, everything that is referencing that is going to be looking at the same values. If we have it so we run a scale on it, everything that was previously looking at that is also going to have its version scaled, even if they were before or after or whatever the version. And we probably don't want that to happen. I don't know if that's a good thing for us. So what we're going to do is take this scale, create a new mesh, and that means we need a new thing to create a mesh. So mesh. And let's just set our points here. So var. Oh, you can't do a var there. Vector 2. That's actually, so one of the things I like to do when I'm defining these things is look for the interface that defines the type that we're storing. In this case, IEnumerable is a good thing to do, and it might actually be a useful way to solve our read-only problem. So IEnumerables are a enumerable set of objects. They're used pretty much every thing that uses an iterator, everything that you can use a for each loop is going to implement IEnumerable. The useful thing with IEnumerable is its only thing is going to be get enumerator, and I think there's a few other things in here. Nope, just getting the enumerator. Which the enumerator is what you use to actually find, is there a next object and what is the next object? It's what's used in a for each. So we don't get a syntax error here. But the cool thing with that is because it's only used to find the next object, it means it doesn't include add or remove or other data structure operations that you might get with a list or something more concrete like a dictionary. This is explicitly just for enumeration. And so by doing that and making our points use that interface, we can actually avoid mutating things too much. And it means that we actually aren't defining the type that we're actually using here. This will just work on anything that can enumerate over vector 2s. Which I don't know. I don't know if that's what we want, but that's what we're getting. So there we go, points. And we'll just do this dot points equals our points. We might want to create a copy of that enumerable, which we can just do with like a new list of vector 2 and just give it the points. And this is actually going to iterate over. There we go. All right, cool. This is going to iterate over all of those points in our list and actually insert them into that new list for us. So this is kind of separating it from whatever this IEnumerable is. The useful thing there is if there are additions to that, or if it's some queue or something, this will only get that state. It won't update and change. And basically what we're trying to avoid here is creating a object that can change around itself without us explicitly giving it an operation to perform. That's sort of what we're trying to avoid. So hopefully this accomplishes that and we get our scale and our split mesh translation. Translation just means moving somewhere in space, translating somewhere in space. So we're just going to do vector 2 with our translation and give it a pretty much the same thing. So we're going to run through these. And instead of this, we're just going to add our scale. Not our scale, our translation. There we go. Cool. All right, so now we have two additional functions that we need to test. We have our scale and our translation. Those are the two operations that we're kind of focused on. Those are sort of the two big ones. The other one is rotation, which is harder. I keep saying that, but it is. So we're leaving that for last because I'm putting it off. So we have our translation, our scale. Let's test those, and then we can get into the rotation because that's also sort of the fun part. It's one of the parts that blew my mind when I was first learning about matrices, and it's why this is called matrix mesh, because I wanted to deal with matrices because they're just cool. So let's add a new test here, and we're just going to call this class called mesh test. Cool. All right, so we have our mesh. We're just going to take some of this. And I don't actually need to do any of that. We can just get rid of this, make this a file scoped thing. There we go. I should say the file scope thing is a .NET 6 feature. So you should go and grab .NET 6 if you want to try that. If you try to use this in other things, I believe like Unity doesn't have .NET 6 to my knowledge. And so if you try to do this there, I think you're going to run into issues and you might get syntax errors from that. So make sure you're on .NET 6 if you're targeting that. If you're not sure, you can check. The easiest way is to just open the project file. I have Visual Studio Code and Visual Studio open because I'm weird. But here is where you would check that. You would just look at what the target framework is, and it should say .NET 6. And you should get some information about what you're targeting. So that will tell you that you're targeting .NET 6. If it says .NET 5 or something else, you probably don't have access to this. Anyway, let's do a mesh test. I don't know if it makes sense to make this. We'll make this public because why not? Typically, access levels, you want them to be as restrictive as possible. One of the downsides of making something public is that once you publish it, you can't really change that public interface or contract that you're kind of forming with whoever's depending on your service without working with all of the dependencies that you have. So by declaring this public, what we're kind of doing is saying that if you depend on this, it's public. Maybe we can say don't use this or whatever, or discourage it. But it's public, so people can and probably will use it if it's their needs. And so one of the things you can do is does this not work? Test must be public. Okay, never mind. Going on different talks about things that I can't change. Anyway, we have our tests. Cool. Let's do using. All right, cool. Using X unit. There we go. Do I need anything else to make this do its thing? I think we just need some theories. So let's just copy and paste because we can. It saves us from typing, so we'll do there. Visual Studio was also recommending facts and stuff already for me, so we can just probably click through that experience. Is that it? Tab. Okay, cool. So it already knows that we're trying to write a test. So do we mesh? Awesome, cool. So we have all of our stuff here. Let's actually define some things. This gets a little bit harder to write inline data tests and theories. So we're probably going to stick to facts. It gets difficult because we have that list of objects that are just big. So I don't know the best way to do that, but we're going to kind of focus on squares. Quads is sort of, I guess, the best name. And I don't actually know what the best solution for this is. So we'll figure it out. I think because what we're doing is I'm going to actually add a shapes class, because that will give us a little bit of help here, both in our tests and in the actual code and application we're writing. So we have an internal class shapes, public mesh quad. And we're just going to provide a new mesh here with a new set of, all right. Vector to array? Sure. Kind of making this up as I go. So we'll see what happens. That kind of got all weird, but there we go. I think I've matched all my curly brackets. Public mesh quad. Oh no. All right, so we're entering the weird curly bracket state. Anyway, cool. So this is going to create a new mesh. I think that should be enough. New expression can be simplified. That's fine. That I think needs a semicolon. I'm confused why it's doing that. Missing parentheses. Good call. Good call. All right, good. Awesome. Thank you so much. Those are the hardest things to catch when you're doing this kind of live coding thing, because you always are like scrambling to find things, and I can never find it. We were missing white space last week. So anyway, thank you so much. Now we need a new quad. So let's do a new vector 2 and create something. I'm going to actually center this at 0. So we have a point at 0, and then we're going to have a point at 1. So x equals 1, point at y equals 1, and then a point at 1, 1. So the advantage of doing this quad, and we'll maybe make a centered one too, because we are basing this on floating points, and everything we've done has been integers. Let's do floats. I've gotten into the habit of just doing actual floating points, so we're just going to actually use floats instead of doubles or something. There we go. Cool. I can just copy this. That would be so much faster. All right, we're going to call this the centered quad. And hit random buttons and get weird things. Cool. All right, centered quad. We get all of this. Now we just need to actually define this one. The first vector is going to be the bottom left, the bottom right. So bottom right, top left, and then just the top. The order of these shouldn't matter because we're just iterating over this and doing that. And as long as we keep the order the same, any use we have of this should be fine. We're doing two different things because when we get to rotations, we'll see different things. If I rotate a centered quad by 90 degrees, it should look exactly the same, just with the vectors in different positions. But if I rotate the normal quad with in the positive axis, it's actually going to rotate around that zero origin. And so we'll actually see it move kind of pivot in space. And so that should give us a little bit of nice feedback that that's actually working. And it gives us a nice test for 0, 0. So there we go. There's our two tests. Let's do a mesh scale test. Now, I talked about testing to kind of define how things should work. You don't need to test every aspect of every part of your code in every test. So in this case, we've already tested multiplication. That is handled here. So we do not need to validate that our multiplication is working. That's kind of outside of the scope of this. What we do want to test is that we're multiplying all of our points. And so that's sort of the test that we want to write. And so we want to be kind of mindful of that when we're crafting our test to figure out how to do this. In this case, we're just going to multiply that centered quad by 2, I think. And we should get something that just kind of works. So mesh scale test. In this case, we're just going to do given a mesh, which is equal to our shapes. Something. Have these been internal public? There. Cool. So we should have access to this now. So let's do shapes dot something. Centered quad. Object reference is required. I didn't make these static. One of the cool things you can do is actually create static classes. So this creates syntax errors on all of our member properties, all the things that would be a part of the class, because you can't actually, once you declare a class as static, the class is static. So everything inside of the class is expected to be static. This is a really nice feature I recommend using if you're building static things to avoid creating objects that have these like weird things that require references when you probably didn't mean to do that. This just turns them into syntax errors, so you catch them pretty quickly. So we get 2 of those and make them static. Cool. Got those fixed. Let's actually scale this up. So we have our shapes, we have our centered quad. Let's create our multiplication, which is going to be vector 2.2. When the result is equal to mesh, and we want to just scale that by the right. We're going to call this something better. Our scale. The names actually make sense here. All right, so we multiply our result by our scale, and now we're expecting a mesh equal to 2.2 or 2. Actually, no, 1. Sorry, on each of the axes. So we have our equality result. We need a new mesh here. Which fortunately means we're going to just define a new mesh. Some of this stuff you probably can write better. Part of this entire project is we're on sort of a time crunch. I gave myself like 10 hours to write this entire thing. So we do kind of have to cut corners in order to do this. We are considering a season 2 to kind of go back and fix or improve or even add onto either side of this application. So we might have something that can consume the meshes that we're processing or send in new meshes for us to process as a next part in this. But there's also opportunities to come back and look at things that we might want to actually analyze a little bit. In this case, mesh new, let's just create a vector2 array. If you're unfamiliar with the syntax that I'm using, which is the inline array syntax, we're doing new vector2 with an array symbol. And then typically you do like, you give it a size and add to it. We're doing curly brackets. And then we can add our new elements here. So we can do new vector2 and give it the size here. So I believe it was -1 and -1. If I could not hit down. There we go, new vector2. And then the order does matter here. We actually care about the order that we're multiplying these in because we're intentionally expecting these to be kept the same. So in this case, our mesh is here. And when we scale this, sorry, we want our shapes. Let's just copy this. That makes things so much easier. We don't need to do any of that. There we go. Cool, done. Okay, awesome. So I'm just going to change these to 1s because we're multiplying by 2. So we expect these 0.5s to become 2s. We are comparing floating points. So there is actually some fuzziness that we could run into here. Floating points are not exact. They're not super precise. It's why you shouldn't represent money, for example, in floating point numbers, because they're based on divisions of 2. So like 0.5 works because it is divisible. It's a divisible by 2 thing. But like 0.1 doesn't because there isn't a convenient way in 32 bits to divide some number by 2 in order to get 0.1. And so when we're talking about floating points and inequality, that can become a complex issue because you might actually start missing things because you'll be off by some tiny bit. I don't think we'll get into that because I'm kind of intending to do like 90-degree rotations so we can kind of flip things and rotate things. Not this, but we'll see. Anyway, there is our mesh scale test. Hopefully this just works. So if we run this, actually, we don't have any quality for our mesh, so this won't work. We also just get vectors here. We don't get the contents of the vector, unfortunately. So maybe there's a way we can improve that. That might be another issue for a later time, though. For now, let's do mesh stuff. So we need to do equality. So in this case, let's just copy what we did for our vectors because that works. So we're just going to grab the equality, grab our mesh, and we're just going to add that here. Our equality operator, we want to test if this is equal to a mesh. So if our 2 things are equal, and then we want to compare these. So mesh. Cool. And then we want this dot points equals, is this, determines whether the specified object is equal to the current object. Is there a link sequence equals? Determines whether 2 sequences are equal by comparing the elements by using the default equality comparator for their type. This might work. One thing we do need to double check is if it actually cares about the sequence of the points. Because if they get out of order, that actually causes other issues in the pipeline. So we want to make sure that translations keep the order of the things that they're doing. So if this doesn't test that, that could suggest that we're getting equality when we actually aren't. And if we're using this in our tests, that could mean that our tests aren't accurate either. So we want to double check that and make sure that it's actually correct. This is supposed to be comparing to our mesh.points. And then let's just double check what this sequence equals thing is supposed to do, because I don't actually know. I believe it's a link feature. Determines whether 2 sequences are equal by comparing the elements by using the default equality comparator. Second, The following code demonstrates how to use sequence equal. Okay, so we have some example code here that's going to kind of walk through whether this is accurate or not. We get two sequences, test if they're equal. They are. And then here, the lists are not equal because we created two new objects of type that do not have an equality thing, so those fail. Let's give it a shot and see what happens. I think this should do what we want. If it doesn't, we'll find out. So I think that makes sense. Let's just give it a shot. If you're unfamiliar, Link gives you it's a .NET C# feature. It gives you a whole bunch of awesome ways to handle data. If you want to work with a whole series of just data points or objects or something like that, any lists, it can handle those and do really cool operations for them. Almost all of them are based off of IEnumerables, so anything that is enumerable is supported by Link, and then you can just use them to iterate over potentially infinitely sized lists to process data. So pretty cool. And in this case, I think it's going to save us a bunch of time because we don't have to write an equality thing for this, where we would have to iterate through both lists at the same time, and I don't want to deal with that, so we're going to avoid it. So there we go. Equals. Does it work? Let's find out. Yes. Cool. Awesome. So we now have a functioning equality operator that can actually test that we're able to prove that our thing is equal. So our mesh scale works for this test. So we know that when we scale something by 2, that all works, and we get an equal result. Now let's actually do that for our translation. So we did scale. Let's make sure we can shift everything. So in this case, we have our centered quad, and I'm going to actually shift it over and to the right in the positive 0.5 direction. Mesh translation. Keep hitting a hotkey to duplicate my line. Anyway, mesh scale, we want translation by our translation. All right. I'm going to type the same word a bunch of times because that's just what happens. And then we get our translation by 0.5. If we do our centered quad, which has negative 0.5, and expect it to find our shapes quad, we should just get the results that we expect. And so we shouldn't need to actually define a new mesh here. We can actually just rely on the defined things that we already have for this test. And I think it should just work. So there we go. So we have a basic test over our translation and our scaling. This actually is intended to kind of confirm that things are scaling and operating in the way we expect. The last thing I'm going to do, just for my own sanity, and because I'm not entirely sure that it checks the sequence direction, it compares that things are actually in the same order. We're going to actually do a translation. We're just going to call it a mesh test. This test is going to go away, so we're going to write this really quick. But in this case, we have mesh centered quad. And what I want to do is get rid of all of this and just create a new mesh. Let's just grab this one. Actually, there's a better way to do this. Let's grab the existing centered mesh, like this, and we can just copy and paste that definition here, and then just move a few of these lines about. So if we put this there, and maybe move this down here, the mesh has the same points now, but they're in a different order. Let's fix that and just grab our mesh. So if these are the same, if the test passes, then we might have some issues because we might be not getting the best results out of these tests. And this is just kind of to confirm that the behavior of that function that we used for the equality is working. We could actually just call this mesh equality test. Cert R not. What's the not equal? There we go. Exactly what you would expect it to be. All right, so assert not equal. We're going to assert that this mesh is not equal to our centered quad. And that should just work. Let's see what happens. That's sort of, I guess, the way we're going with this is just seeing what happens. It passes. They're not equal. That's good. I'm paranoid, so we're just going to double check this. Just because I like to see tests fail when I write them. Because if your test always passes, if it's always been passing ever since you wrote it, and it continues to pass, maybe that test isn't actually that useful, or maybe that test isn't actually working. Tests are typically only useful when they're failing. That might be an overgeneralization. I can roll that back a little bit, but the useful part of a test is those failure cases that tell you this isn't doing what it's expected to do. And if you have a test that you always expect to pass, or should never fail, or not should never fail, but does never fail, maybe that test isn't the best test for whatever surface you're testing. You probably want something that is going to fail at some point. That is going to give you those signals that, hey, this isn't quite working. Or if something is constantly failing and you don't have tests for it, maybe add them. Anyway, we're going through a bunch of testing stuff because testing is important and also hard. For me, maybe we're not getting into some of the hardest bits here. Unit tests tend to make things be the easier side because you're testing such a small scope. You're just testing one function or one thing. Once you start expanding that scope into those integration or end-to-end tests, you're testing an entire application. And there's a lot that needs to happen for an application. For ours, if we wanted an end-to-end test, we would need to set up 2 queues. We'd need to set up our application and get it running. And we need to actually insert messages into those queues and read messages off of those queues. But we'd also need to make sure that nothing else was doing that, because if those queues had other things writing to them, then our tests wouldn't necessarily pass because we'd get noise. It can get complicated. I guess that's sort of what I'm getting at. And so here, keeping things simple and giving as clear a signal as possible is good. So in this case, I have given an expect. We're actually going to add a little bit here just so I know what's going on, because this isn't entirely clear why this is a test of equality. We're just going to say expect meshes with points in different sequence order to not be equal. Right, and there we go. This might need some refactoring actually to make it a little bit clearer. We call it mesh equality test. That isn't what this is. Mesh equal in point order. All right, naming's hard. We're gonna call that good, but that I don't like it. Anyway, let's do rotation, because we've done all the easy stuff. So let's do the hard one. So rotation is cool. I mentioned that matrices are sort of how all of this stuff in 3D graphics is how a lot of this stuff happens. You could do the translation and the scale in a matrix as well. And it would kind of condense everything, because we just have that one thing that was doing all of it. And we just need to create different matrices that could define how we wanted to do all of this. That works, but they're complicated. And it's a little bit easier to just add 2 vectors than it is to multiply a matrix by a vector, because that's what we're going to kind of build into. So before we get into that, we're going to kind of look at this. So this is the complicated bit. We're gonna just pull up Wikipedia because they actually have some good diagrams of this. You don't need to know this. That is not the point of this. This is just to kind of cover this, and also why tests are useful, because this is, I don't understand it. Yeah. Anyway, we have different rotations. This is for three-dimensional objects, doing rotations around the X, Y, and Z axis. That is going to take some cosine or sine of a degree and rotate that entire vector by that around the origin point, so 0, 0. These are for 3D, so we're going to skip up here to the slightly less scary versions, which are here. I believe this is for a clockwise rotation, so I think that's the one we want. I had it pinned, but then I lost it. So this is what we want to do. Vectors or matrix multiplication is basically this. This rotates column vector. So column vector is your matrix or your vector 2. We need to create a 4-dimension or a 2x2 matrix that defines our rotation. So that's the next thing we want to do, and we're going to open Visual Studio for that. This is intentionally like trying to inject a little bit more complicated stuff, just so we have some more testing patterns, and also we kind of complete the 3 operations. But this is definitely the most complicated one, and also the one that is just hard. So we're gonna just do matrix 2x2. I'm doing 2x2 matrices. So you might see people add an additional dimension. So for 3-dimensional vectors, you might see a 4-dimensional matrix and vectors. That we're not gonna. This isn't a graphics class, and this isn't like, this is hard math. I want to be very clear about that. We're doing this because it's intended to kind of give those tests and hopefully kind of expose some of the cool stuff that is going on behind the scenes in some of your favorite games or in some of your other favorite other stuff. We're kind of looking at that. So matrix stuff. Let's do public float, and let's just give it a 2x2 matrix. So we're just going to do a I don't know what I want to call it. Let's call it matrix 2x2. I don't think that's how you define those, so we're gonna skip that and do a new float 2x2 matrix or 2x2 array like this. I need to define this a little bit better. There we go. All right, cool. So we get our matrix defined 2x2. This gives us effectively a 2-dimensional array that has 2 dimensions, each with 2 values in them. So we have that 4 value value matrix. There we go. That's the word I wanted. Yeah. Let's actually do some of this. So matrix, do that. Let's create a new matrix 2x2. And we're just going to, I don't know the names for these, so we're just going to call it R1, 2, 3, and 4. That might not be a good. Those aren't good names. I need to come back to this and figure out how to name these things. But this will be enough for us to kind of get that started. And so we're just going to create a public. This shouldn't be public. Let's create private float there. We're not going to expose the actual inner workings of this out. So we're just going to create something that can do this rotation. That's all we're trying to do here. So that's what we're going to focus on. Is our new matrix, which is going to be our 0, 0. Put that equal to R1. All right. Sorry, I'm thinking a little bit because I don't actually have a plan for how to lay this out, and it might get complicated. So thinking about that. For whatever reason, I thought it was a good idea to insert some linear algebra into this intro to cloud computing thing. Anyway, we're going to ignore that and pretend like this was a great idea. So we get those 4 values. So we have our values set in our matrix. Our values aren't a thing. I just used R because I couldn't think of a name. Those values are going to represent the rotation. The way this works is we're going to take a vector and multiply it across this matrix. So for the vector, it's actually going to be formed as a column in that matrix. So if you're unfamiliar with matrix multiplication, I guess we're going to talk about that. So it works by multiplying the rows and columns of the matrix by the other rows and columns of the other matrix. So the rows of one get multiplied by the columns of the first. And that's sort of how you get the result. So in this case, we're not going to do matrix multiplication. We're intentionally keeping this very targeted. Also, we're not building a math library. That is not the goal here. We're just doing this so we can do rotations. And so to do that, we're going to also create a static rotation matrix. This will give us a way to actually define this new thing that we want. So let's give it a float of our rotation. And then let's grab this. Cosine, negative sine, cool. So we need to actually figure out where these things are going. So in this case, I'm going to use X as the columns and Y as the, use X as the rows, columns. So I'm getting confused. Let's just type this out. That'll be way easier. There we go. Cool. All right. So we have R1 as that position, and R2 is in the second column. So R2. And then this is going to be R3 and R4. This is where my names don't make any sense. I'll think about that. I don't have an answer here. So rotation matrix is going to do this. We need to return a new matrix 2 by 2 with these values in it. So those are going to come directly from that formula. So I believe it's math.sine, mathf. Where's that coming from? I don't know this class, actually. Hold on. .NET mathf. Is this a new thing? Did I miss this? I don't actually know. Anyway, that we can skip over most of this, but what this is going to do is give you floating point results. I believe the normal math libraries give you doubles. We're using floats. So this might do that without us having to do a bunch of casting and rounding and other stuff. Does it support sine, cosine, singles? Cool. If you're unfamiliar and you see single in the documentation, that's float. Same things. They mean the same. This is just the class name of the float. So let's work with that. So here is our formula, which is cosine and sine on the two sides. So let's do that. We had cosine, and then we had negative sine, and then sine and cosine. All right, cool. Just to make sure I have everything in order, cosine of our rotation and cosine of rotation. All right. Fun typing bit. So we get all of these plugged in, and then from here we'll be able to actually implement the multiplication bit, which hopefully isn't too complicated because we're just taking a matrix times a float and getting or matrix times a vector and getting another vector out. So we can kind of cheat a little bit because that's sort of how this is all designed. We need a return type here, matrix 2 by 2. There we go. So that gets us our matrix. We can generate that new matrix to rotate things. And then basically what this is doing, what this formula is doing is giving us something that given any point, it is going to take that point and rotate it by a specific amount. This is using trigonometry to do that by taking the cosine and sine of our points. The location of that point is actually going to change depending on the result of that. And that will actually figure out where things end up. So that's what's going on here. I think we're good. This public new, what am I doing? There we go. All right. Defining an entirely new syntax. So we have our matrix, we have our rotation. Let's actually do our multiplication. So let's do public static vector 2. Let's call this a rotate function. Again, we're focusing on the thing that we're doing, not the fancy math stuff. So we're going to do rotate, and we're just going to give it a new, not a new, what am I doing? We're going to give it the vector 2 of our position. Point's a better name. Point, and we're going to give it the float, which is the rotation of this object. One thing I don't know is if those sine and cosine are radians. Okay, they're in radians. That's something we want to note. Rotation is the radians of rotation. That's good to know because if we give it pi, or if we give it like 90 degrees, that is not the same thing. So we just want to make sure we're on the right track here. So we have a rotation. We're going to generate our rotation matrix from the rotation, like this. Cool. I'm using the same name a bunch. So let's call this our matrix. That'll work. And then we need to actually multiply these two. So in this case, that is going to look like, is this priv? Yes. Okay, cool. So we're just going to actually just do this here because we can just type it out. So if we do return new vector 2 of our rotated vector. So in this case, we have our x and our y. So we can do point.x times whatever the matrix stuff is, plus the other one times that, and then do our point.y, and do all of the matrix multiplication there. So we are going to figure out how to actually do these things because there we go. All right. So we're just going to pull up the formula for matrix multiplication because I can never remember it. And do this and hopefully get some good tests out of this because I lost the formula. I'm trying to figure out if it goes horizontally or vertically, columns and rows. I think it should be or horizontally. So let's do that and see what happens. So in this case, we have point.x needs to be multiplied. Our x coordinate is going to be here. And our y coordinate is going to be here. And we're just going to multiply those. So in this case, x needs to be multiplied by these two things and y by these two things, if I am correct, which I think I am. It's always the paranoid part of me that thinks I might be wrong. So let's figure out how to do that and make sure I'm actually thinking about this right. Apologies if there's a little bit of noise. They're doing yard work and now there's a plane. So things are conspiring to make my mic not work. But let's see here. Multiplication C is equal to, sorry, trying to figure this out. Cij is equal to the iteration of that. So this is really hard to look at when you're doing this. I actually probably should have had notes for this. Just saying that now. I think this is easier. So we do those. Whoa, do those, and these get multiplied. All right, cool. And then the results get added. So we should. All right, go here, and we're just going to do point.x and point.y. Again, cool. And let's actually do this multiplication. So we get matrix R4, which is actually at 1, 1 times this, and our matrix at 1, 0. Okay. Is that how we're doing this? We have R3, R4. Yes. Okay. Cool. The fun part, like I was saying. So we get this. This is going to be our 0, 1. And our 0, 0. Awesome. Cool. So this doesn't work because I actually need to reference the actual matrix. So let's just grab that. There. So we're just going to actually grab the actual array that has all these values, so we can just do this and get a result, because that just makes more sense. And then this is not happy because I'm missing a semicolon. There we go. And let's break this up a little bit so it makes a little bit more sense. And there we go. So that, hopefully, if I've done that correctly, is going to give us a 2D rotation in space. And if not, then I've screwed up, and we'll figure that out as well. So this is the part where testing becomes useful because we've gotten into this more complicated thing. We should expect this to rotate, for example, clockwise, or I'm going to give it a 180 degrees. I'm just going to give it pi, which is a half rotation. So we should expect to be able to rotate an object into the negative space, if that makes sense. So what that might look like is this. And for whatever reason, I didn't think that I would have to do all this mental math. So let's just test this. Mesh class. We want to rotate our mesh. So let's add a function to rotate. Public mesh rotate float rotation. The rotation of the mesh in radians. Cool. This will give us a way to kind of rotate this. Let's capitalize that and grab this. One of the things that I kind of stick to is if you're multiplying something, or if you're copying and pasting multiple times, like we've done now 3 times, that can be a good indication that that some abstraction might be useful. Because we're doing the same thing over and over and over again, we're creating a bunch of duplicate code, which means as we come back to maintain some of this, we might update one function, but not all of them. And so inserting an abstraction can help us address that and make sure that we kind of keep everything doing exactly what it's supposed to, instead of getting some weird differences. So rotation. I don't know if we want to rotate like this. So part of the thing, I wrote rotate so we can rotate a single point by creating a new matrix and then rotating it. If we do that, we're creating a new one every single point that we want to change. That might not be ideal. So let's do this. Matrix. Cool. And then we can get rid of that point. Yes. All right. Cool. And this becomes a little bit less fun. All right. There's our matrix stuff, and we should have enough time to kind of finish up this. What? Okay. Vector 2. So give it the matrix the point, and then we get something new out. Awesome. Rotation matrix equals a matrix 2 by 2. I'm actually going to make this so this can't be initialized. So we're actually going to prevent constructing this. So I'm going to protect it. Protected. And so this is going to make the constructor not visible to things that are not directly inheriting from it. So there is no constructor for this object anymore. So if I try to do new something, we should get an error here that is going to prevent us from doing that. Constructor doesn't take zero arguments, which should be fine if we give it 4. It should still fail. Not accessible. So that kind of can keep us from doing weird things. Instead, we're going to use the helper functions because we created them, and just create something that can rotate like this. And then our point is just going to be multiplied by our rotation matrix. So we do our stuff. But you got rotate point. All right, cool. All right, so this is going to rotate our point by the rotation. And then the entire point of that refactor is to avoid recreating this rotation bit over and over and over and over and over again, because that's what would have happened. And we should spell this right. There we go. So we get everything spelled, get everything compiling. Now we just need to get everything tested. So we have our mesh. Let's test that here, and just add a rotation test. Mesh rotation test. And so we get all this. We should now just be able to rotate this. So rotate by some amount. So we have our shape, given a shape, and the rotation. Let's rotate by 180 degrees is I think what makes sense. And then I'll just have to figure it out. So let's just do mathf.pi. Is that the correct thing? I think so. All right, so pi is defined, that'll be 180 degrees, but it's not going to be a flip. We're not scaling this by -1. We're actually rotating this. So the points will actually be in rotated clockwise 180 degrees. So we need to figure out what that is actually supposed to be, because I don't actually know. So now let's go and grab our shapes and grab our quad and figure out how these results should look. Mesh test, cool. Our expected result is here. That's actually something to keep in mind. The expected is the first value, and the result is the next one. So whatever you got in your test should be the second value. I don't think it matters really. It just gets a little bit confusing because the actual printed out results will say expected something. And if you have the order wrong, that won't be correct. So vector 2, let's figure out these. We're rotating 180 degrees. So what that should mean, if I remember correctly, is that this should be like this. I think. We'll see if this works. And so there we go. We have -1. We've rotated everything. I do have my own Twitch channel. I have primarily been a YouTuber. So I've done a little bit on Twitch, especially during like game jams and hackathons. I will stream that. But like I said at the beginning of the stream, a lot of my focus is on the reactor stuff I'm doing right now. Mostly just because time and I'm moving and there's lots of stuff going on, so I need to focus. So for now, most of it is on the reactor stuff. You can go and check out there in the chat. There should be some links to the reactor pages, and you can actually see some of the sessions that I have coming up. that will go into a bunch of different things. We have some things looking at different career paths you can take in technology. Also some like game dev stuff to kind of get you introduced to game dev, and also games as a service. So if you want to learn more about like building cool online game stuff with Azure PlayFab, we're going to be taking a look at that in January. So some fun things to look forward to. But yeah, I also tinker at other things. Anyway, hopefully this rotation works and it comes up with something. If it doesn't, we should get some useful results back out of this that'll tell us that it didn't work. Or we'll get this. So we're getting empty vectors that don't say what they have in them, what values are inside of them. So I don't actually know what the results of this are. I think the best way to look at this and figure out what the heck is going on is to actually run this and see if we're getting something. What we should see is solid values. We should see like ones and zeros. If we start seeing floating point values when we test this, if we run a debugger against it, I've screwed up the math entirely. And we'll see. My plan is to expand this into 3-dimensional space, probably just over like sometime before tomorrow, just so that we can kind of focus on that. I scoped this down out of that for this session, just because we're almost out of time and we've only done 2 dimensions. So, those don't look right. Oh, because they're not. There we go. Let's multiply that by the right thing. Also, I had mentioned floating point stuff can be weird. We're actually seeing that here. So I don't think this would work even if I did have everything correctly for this specific value. Because what's happening here is we are actually getting, oh, that actually worked. Mesh to rotate, this result has a few different points, and they have like 0.499999997, which is not 0.5 like we might expect. That means that our floating point numbers at some point didn't quite line up, and now they're kind of off. That's a good example of why you shouldn't use money with floating points. There is a decimal value that you can use, which is probably what you want if you're doing that. And that doesn't use floating points. But if you use doubles or floats and you're storing anything that is expected to have a constant value, that might change if you start doing multiplication or division on it, or even just other stuff. It might not quite align. So something to keep in mind. The value you're off is off by a fraction of a really small fraction, but it's still off. It's not the exact number. So if you're expecting equality, I think there's actually a function for that, which I never remember, but I think math f dot something, like a prox, I think, math dot. Well, we don't have time for that, but anyway, there's a function for that. Maybe it's float. Getting distracted. But I don't see it. All right, it's fine. Epsilon is. Let's not go into it. There's a bunch there, and more than I have time to talk about. But it's a thing, and we might run into it here. So that's why I'm calling it out. It's not just trivia. At least it might not be just trivia. We'll see. It still failed. All right, cool. Let's actually run the debugger. I skipped the debugger there just because I was kind of hoping it would just work. You probably want to see what happened anyway, but this will let us get a little bit deeper into this. So we do get the first point is 0, 0, which is good. That means it worked for that point. So I didn't screw that part up. That's good. The next point is off by a very small amount in the -1, also in the opposite space. So I might have those two vectors flipped I'll need to double check that. And then the other one is also off by just a tiny small amount. So we're almost there. It almost worked. Let me just figure out if I can sort this out. So we have our shapes. If we rotate this 180 degrees, so x equals 0, yeah, this should be negative. Okay, that makes sense. I just wasn't thinking about that right. So these are flipped. But it is working. It's just not quite working. So we have about 10 minutes left to kind of wrap this up before we end. We will be back tomorrow. I believe we aren't streaming the continuation of this on Twitch tomorrow, but we will be back on Thursday. If you're watching on YouTube, it should be there. Or if you want to just catch these later, you can check out the YouTube Microsoft Reactor channel, and you'll be able to catch all the videos or previous things that I've done there. So highly recommend. There should be links in the chat. Yeah, so there's links in both chats if you're curious. So there we go. Let's see here. Here's all of that. This is still going to fail because we have that off by a bit. So let's see if we can fix that. I don't know if we can, at least not quickly, but we're going to try. So mesh has equality points. All of the equality comes down to our vector2 stuff, which is here. In this, we are using equality to compare floats. And that's because of this off by a small fraction thing, that's typically not what you actually want. Typically, you're going to want some float .net prox. I think this is what we want, floating point, numeric types. We'll double check. I didn't see anything there. All right, cool. I don't see it. I was approximately equal, and we get to learn how bad at spelling I am. There we go. Float extensions approximately. Is that just a thing? It's in that's not in our project. So what else compared to? Yeah, I think that's sort of what we're looking at, is kind of doing the thing. What I'm used to is coming from a Unity background. That's where I kind of learned a lot of like programming, and also that's where this entire perspective on this problem is coming from, is from sort of that indie game developer perspective. I'm used to this math.approximately equal. I think there's a way to do that, but we're just going to implement our own and be close enough. So in this case, let's just do, what's the best way to do this? Let's do math. We'll just use J Litter's suggestion, which is to use math.absolute value and take the absolute value of the difference between the two things. So in this case, we're just subtracting one from the other. And then instead of saying, is this equal to 0, because that's what we would expect the difference to be if they're equal, we're going to say if that is less than some value. And we can do that for both of these. Math, that absolute value of vector. That. I don't need to rewrite that. There we go. And then we can subtract these, say less than, and we're going to just add a constant here of floating precision. I don't know if that's the best name for it, but that's what we're going to use. It doesn't exist, so we're just going to define it up here as a private constant value. Floating precision equal to 0.01, I guess. That's probably way too big for this use case. It needs a type. Can't forget that. All right, cool. So we give it a type. And what this is doing is subtracting one from the other, effectively finding the difference between the two values. which should be some really small value, and then saying, is the absolute value of that less than this thing? So we take the absolute value because if something is negative, like -5, for example, less than would obviously catch that, and we don't want that. So instead of taking the absolute value, we're just looking for really small differences from 0. So the difference between these two is relatively small. Then we're good. And again, this is way too big. So let's shrink that down a little bit. I think you might be able to use like epsilon for this. We have 4 minutes before I'm supposed to finish this. So let's see if we can do that quick. .NET float epsilon. So epsilon is the small number that can be represented by floats. That's the intent of it. So it's really small. I believe it's, the smallest positive single value that is greater than 0. There might be a way to use that in an approximate function, but I don't know if there is off the top of my head, so we're going to skip it. But that's there if you want to explore that. But yeah, floating points are fun. And hopefully, fixing this, we now have running tests, and we can actually run this and get a pass. Cool, and we can. So everything works, which is better than I expected. Good. And all of our tests pass, so our entire project is green. So we're in a good spot. All of this stuff is functioning, and we can kind of work with two-dimensional things to rotate, scale, and translate them in space, and kind of move them about and do that stuff. The next thing we need to do is figure out how to actually process this stuff. And so what that's going to turn into is a set of commands for this application. We've been focusing on the class library, the thing that is actually kind of doing the math. Now we need to focus on the thing that can actually handle the data processing, that can actually do a lot of this stuff. So in this case, we're going to probably look at that tomorrow and figure out how do we want to ingest data into this pipeline, and how do we want to structure that data? What do we want that request to look like? That's going to be what we're doing tomorrow, and kind of figuring that out, and hopefully getting sort of started on the cloud path of this whole thing, so we can actually start integrating cloud components and actually start doing things with the cloud. So we can actually make a real service out of this, rather than just a set of tests that pass. Turn this into something that is actually functioning. But yeah, that's sort of where we're going. Eventually, what I'd like to do is have this whole thing kind of structured. So you could take, for example, this cube, pass it up to our online service, process it through, do whatever processes you need, whether that's scaling it or removing duplicate values or doing something else. Don't know what those might be. We're not going to get to a lot of those more complicated things in this session, like series of sessions. But you could do that and then pull it back down and maybe ingest or pull it into somebody else's game or something like that, or process some texture or something. That's sort of the visualization of this. And it's something that you can kind of apply anywhere when you're designing applications. This isn't just something tied to games. You don't need to really care at all about the games part of it. It's just games are cool. So that's sort of what I'm trying to use to kind of build on this, and we can kind of go from there. But here we have these, so you can kind of play with it and hopefully build something out. We're focusing mostly on the pipeline part. So yeah, I think that's mostly it for now. So I will leave you all here until tomorrow, and then we can pick this up and do cloud stuff with it. But yeah, thanks so much everybody for joining, and hopefully this was interesting and you learned something.
Thanks so much, Sam. As Sam mentioned, we will not be on Twitch tomorrow for the stream tomorrow. It will be at the same time, 3 p.m. to 5 p.m. Pacific time. But you can find us tomorrow on the Reactor YouTube channel. I've shared the link a few times to this series page where you can go and register, and then you'll get the live link. And I also, earlier in the comments, shared the link just to the YouTube episode tomorrow. So we hope to see you there. We will be back on YouTube and Twitch for Thursday's part 4 session. Thanks again so much, Sam, and hopefully we'll see everyone tomorrow.
Awesome. Thanks, everyone.
Have a great rest of your evening or day. Bye.